everybody, welcome back. Mr. G here again. In the next lecture series for Tech 101 electric circuits, we're going to be looking at combination circuits. So a combination of a series and parallel circuit. So part of it's going to be series, part of it's going to be parallel. So let's take a look and see how this is done. Over the last couple of lectures, we have looked at resistors connected in series. So we know that resistors are in series because they share the same current. We also looked at resistors in parallel. And we know resistors are in parallel because they share the same voltage. In a series circuit, individual voltage drops add up to the total. So V1, V2, V3, and V4. And that is Kirchhoff's voltage law for series circuits. In parallel, we know that the individual branch currents, I1, I2, I3, all add up to I total. So that is Kirchhoff's current law for parallel circuits. Now, that's all really self-explanatory now that we know what series is and we know what parallel is. But in a real-life circuit, we actually find combinations. So that means that there are some resistors that are going to be in parallel with each other, and other things that are going to be in series with each other. And we have to figure out how to solve these particular circuits. Because all of these rules apply. So all of these rules apply to the series part of a combination circuit. These rules apply to the parallel part of a circuit or combination circuit. So for the series, remember we looked at R total is equal to R1 plus R2 plus R3, etc., etc., etc. And we looked for parallel, we looked at R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Again, all of these things are in a combination circuit. So the series laws work with the series part of the circuit. The parallel laws work with the parallel part of the circuit. So the tricky part is to identify what is the series part and what is the parallel part of a combination circuit. And then we have to solve for them like we've been solving for the other circuits. So calculating currents and voltage drops and all that kind of stuff. But what we need to do is we need to break down these circuits. So what I'm going to do is I'm going to put some numbers onto this one and turn it into a real circuit. So we have parallel and series combination. So we'll call this one R1. We'll give it 1K. We will say that this is R2 at 2K and this is R3 at 3K. then we will say that this is V total, and we will give V total 12 volts. So when we solve for this circuit, we're going to be looking for all of the same things that we looked at for the other circuits. So we want to find R total, I total. We want to find VR1, VR2, VR3, IR1, IR2, IR3. So let's identify this first. R total is of the whole circuit. So from this point to this point, that whole circuit, that's R total. I total is the current leaving the source, just like in all of the other things we've been working on. VR1 is the voltage drop across R1. VR2 is the voltage drop across R2. VR3, voltage drop across R3. IR1 is the current going through R1. IR2 is the current going through R2, and IR3 is the current going through R3. So that's what we're looking for. Now hopefully you can see already an idea of how these things are getting connected. So the idea is, in this circuit, there are some parts that are going to be in parallel. Those parallel parts must share the same voltage. Then there's going to be other parts that are in series. Those series parts must share the same current. So how do we solve for something like this? Well, first of all, what we need to do is we need to find R total so that we can find I total. Now, how do we find R total of a combination circuit? Well, what you need to be able to identify is, does this circuit simplify down to series, or does this simplify down to parallel? Because there's a combination in both. There are some parts that are in series, there's some parts of the circuit that's in parallel. But when we simplify the circuit down, does it simplify to a series circuit, or does this final simplify down to a parallel circuit? When we're looking for R total, this is important, because with R total, if it's series, we've got R plus R plus R, etc., etc., etc. If it is in parallel, we've got 1 over R plus 1 over R plus 1 over R, etc., etc., etc. But when you look at this circuit the way it sits, we do not see just a series circuit. We do not see just a parallel circuit. We see some of both. So the idea is to simplify this down so that you can apply one of these rules. The question becomes, how do you simplify it down? And which one of these does it simplify to? Now, one easy thing, if this is going to simplify down to a series circuit, and this rule does not apply to every combination, but it applies to a lot of them, the first thing you want to look for, does I total flow through any single resistor? Oops, single resistor. If you answer yes to this, then this circuit simplifies down to something that is series. Down here, does any resistor have the same voltage as the source? So as V total. If you can answer yes to that question, then your circuit will finally simplify down to parallel. Now again, these two little things to look for are not the perfect solution for every single circuit, but they do work. It's a first step. So, does IT flow through any single resistor? If you answer yes, this would simplify down to a series circuit. If you answer no, then you go, does any resistor have same voltage as V total? If you answer yes, then it's a parallel circuit. If you answer no to both of these, then you've got a little bit more of a complex scenario. But here are the first two starting points. So, if I go back to this circuit, I can see that I total leaves the source and it flows through R1 before it splits. So it splits here, and some goes this way and some goes this way. So because the current splits, we know that we have some kind of a parallel combination here. Because I total flows through this resistor, we know that we have some kind of series circuit as well. So what we're going to do is we're going to answer these questions. Does IT flow through any single resistor? Why, yes it does. So this simplifies down to the final step of being a series resistor, our series circuit. So therefore we can actually add our resistors to get our total. But how does it simplify down? So let me just put this up here and bring out another paper. We're going to go through step by step on how to simplify this circuit. So we know from this statement that this thing ends up being a series circuit. So that means that the parallel or the power supply and this is R1, but we don't know what this is. In this circuit, I've got this parallel part. Now we know these two resistors are in parallel. Why? Because the current splits and they share the same voltage. So notice that if I had a voltage drop here, whatever it is, it would be the same as here, because these things are connected in a parallel scenario. And the current splits at this point. Some goes through this resistor, some goes through this resistor, and then they rejoin and flow back down to the source. So this part of the circuit is parallel. So what we're going to do is we're going to extract that part of the circuit by itself. So I'm going to take that out, and that looks like this. Where this is R3 and this is R2. So what I'm doing is I'm extracting that part. I'm going to find out what the resistance is of that parallel circuit. So just those two resistors in parallel. We've got a 2K and a 3K. So our rule was product over sum. So 2K times 3K divided by 2K plus 3K. 5K. So that equals 6. $1.2K. So, if I have a 2K resistor and I have a 3K resistor in parallel, the equivalent of those two together is 1.2K. So this was 1.2 kilo ohm. Do we know that makes sense? Yes, because those two in parallel, the replacement or equivalent resistance of those two must be smaller than the smallest one. The smallest one is 2K. 1.2K is smaller than 2K. So, what I found is by extracting that parallel part out, I can find what they call the equivalent resistance of that network. So, resistance A to B. This is 2K, this is 3K. Resistance A to B. Those are equivalent. So if I was a power supply that was connected from A to B, the current that I would send down the line would be the same current I would send down the line here. So these two resistors in parallel equate to this one by itself. So again, what we did, I extracted these two resistors out. I found what the equivalent would be. And now I'm going to go back to my circuit and I'm going to replace these two with the equivalent. So, if this was point A and this was point B, this is point A, this is point B, I am replacing what we refer to as R2 in parallel with R3. I am replacing them with one single resistor, which is 1.2 kilo ohms. So that means that this becomes 1.2 kilo ohms. This one was 1 kilo ohm. Our power supply was 12 volts. So again, what I'm doing is I am simplifying the circuit. When we asked ourselves these questions, does IT flow through any single resistor? The answer was yes. So that means that this circuit simplifies down to series. I total flows through this resistor before it splits. So therefore, this circuit must simplify down to series. So now what I need to do is I need to replace this parallel with an equivalent resistor so that this circuit translates into a series circuit, IT. So now, let's cover that up so I can make some space. So now we're going to bring in this stuff. So what is R total of this circuit? Well, R total of this circuit is exactly the same as R total of this circuit. Why? Because we just replaced this part with something that is equal to it. So therefore, R total is equal to 1K plus 1.2K. So that's 2.2 kilo ohm. So what we've done, again, is replace these two resistors, that's the parallel part of the circuit, replace them with an equivalent resistor so that we can simplify the circuit down into something that is series. Now our rules for series circuit supply. We want to find out R total, we add up all the resistors. Now we want to find I total, we have V total divided by R total according to Mr. Ohm and his law. So that's 12 volts divided by 2.2 kilo ohm. So 12 divided by 2.2K, 5.45 milliamps. 5.45 milliamps. So now we know that I total is 5.45 milliamps. We know that I total is 5.45 milliamps. So now, what else do we know? Well, we know that I total flows through this resistor. We know that I total flows through this resistor. We also know that I total flows through this equivalent. So, we can use Ohm's law and we can find out the voltage drop across this resistor. So voltage drop across R1 is equal to, in this case, so I total is the current that's flowing through that resistor. So there we go. It's I total, which is equal to 5.45 milliamps. So basically IR1 times R1. So that becomes 5.45 milliamps times 1K equals 5.45 volts. I'm just doing my best to keep this all on the same page for you, or on the same screen. So, I now know that the voltage here to here is 5.45 volts. I know that my V total was 12 volts. I know from Kirchhoff's voltage law in a series circuit that all of the individual voltage drops must add up to the total. So I can find the voltage across these, or this equivalent resistor. So according to Kirchhoff's voltage law, the voltage across the 1.2K resistor is equal to V total minus the voltage across R1. So therefore it's 12 minus 5.45 volts. Therefore we end up with, so 12 minus 5.45 volts, 6.55 volts. So the voltage across this 1.2K resistor is 6.55 volts. A to B, A to B. So we know that the voltage across the equivalent is 6.55 volts. That voltage there across the equivalent would be the same as if I went over here and drew this picture. So that means that voltage from here to here across that one blue resistor is equal to 6.55 volts. And you will also notice that that voltage appears across R3 and R2 because they are in parallel. So let's go over here. VR2 is going to be 6.55 volts. Why? Again, because we calculated 6.55 volts across this resistor here, the 1.2K. Where did that come from? It came from the equivalent of these two. So that blue one that I drew in there. So we take a step back. Where did that blue one come from? It came from these two in parallel. So that means that the voltage that's across that 1.2K is also across the original resistors that was derived from. So now we have voltages, we have resistance values, we can actually calculate current, Ohm's law. So Ohm's law, VR2 divided by R2, VR3 divided by R3. 6.55 divided by 2K. 3.275 milliamps. 3.275 milliamps. For IR3, it's that voltage, 6.55 divided by 3K. 2.183 milliamps. Now, I total 5.45 milliamps flows out of here. It goes through that resistor, then it splits before it goes through these two. Kirchhoff's current law for a parallel circuit states that if I add up these two, IR2 plus IR3, they should give me I total. Well, let's take a look. Because I total is flowing to this point, then it splits. Some of it goes here, some of it goes here, and then it reconvenes together and comes back down to the source. So whatever flows through this branch and whatever flows through this branch must add up to be I total. So if I did 3.275 milliamps plus 2.183 milliamps, I get 5.45 milliamps. So that's how we end up solving one of these combination type circuits. So again, what we have to do is find equivalents. So we found an equivalent resistor that was the same as the two in parallel, and then substitute it into a series circuit. And then what we did is we did some calculations and then worked backwards. So we had to put the circuit back together in steps to calculate the rest of the values. So we're going to be going through a whole bunch of these over time. But again, the idea is to identify what kind of circuit it simplifies down to. In this case, it was series circuit. All right, now we have the other type. So here's another example. Again, this is a combination circuit. There's part of it that is series, there is part of it that's parallel. What we want to do is we want to be able to, again, solve for everything in this circuit. R total, I total, VR1 VR2, VR3, IR1, IR2, IR3. So all of the voltage stuff, the totals, all of the individual stuff. So in order to do that, we must again simplify the original. So I'm going to bring back our little questionnaire. We're going to ask our questions. Does IT flow through any single resistor? Well, let's identify this stuff. Same as what we did last time. Here is I total. R total would be the whole circuit. This is IR1. This is IR2. This is IR3. This is VR1. This is VR2. And this is VR3. So let's bring back our questions. Does IT flow through any single resistor? Well, it leaves the source and it flows up this way, and then it splits, and some goes this way and some goes this way. So the answer to this question is no. There's no single resistor that has IT flowing through it, because it splits. All right, let's move on to the next question. Does any resistor have the same voltage as V total? Well, here's V total. And I follow these lines up. And if you look, this resistor has the same voltage as V total. Then I follow it up. This one plus this one equal V total. So they do not have individually V total. Together they do, but individually they do not. But this one does. So does any resistor have the same voltage as V total? The answer to this is yes. R3 is connected directly across the power supply. So this circuit will simplify down to something that is parallel. So what does that look like? Well, here is a parallel circuit. So this would be V total. Now, how do I know that we have two resistors in parallel? Well, I look over here and I see we have two branches, one going this way, one going this way. So the equivalent is going to have two branches, one going this way and one going this way. So this is R3 because it's connected directly across the supply. And we know that the current through there is IR3. And here's our I total. Now we have to look at this resistor. This resistor is coming from the other branch. So what we're going to do is extract that other branch, just like we did before. I'm going to extract this other branch and I'm going to find its equivalent. So I have these two resistors, R1 and R2. This one is 1K, this one is 2K. If I needed to replace these two resistors with one single resistor, so from this point to this point must be equal, I know that these two are in series, and if I'm going to replace them with one equivalent, I just add them up. 3K. And that is the equivalent of those two stuck together. So that means if I have a power supply and I have this resistor and this resistor, it is the same as this. So if this is 1K and 2K, the equivalent is 3K. That means that they would draw the same current. So they are equivalent. So what we're doing is extracting these two out of this circuit and finding an equivalent. Once we do that, we take the equivalent and put it here, 3K. Now you can see we have a parallel circuit. We know that R3 is 3K. We know that the equivalent is 3K. So now, again, just going to bring this back. R total of this circuit is equivalent to R total of this circuit. So in this particular case, we've got 3K and 3K. So we can use our 1 over formula, we could use our product over sum formula, but lucky for us, both of those resistors are the same value. So we've got that third rule. Take the value of 1, divide by however many you have, and that is your equivalent total resistance. So now I have my total resistance. I use my total voltage and my total resistance to get my total current. So this was 10 volts divided by 1.5 kilo ohms. My current flowing in this circuit is 10 divided by 1.5 kilo equals 6.67 milliamps. 6.67 milliamps. All right. Now, what else do I know? Well, I know that V total is across R3. So the voltage across R3 is equal to V total, which was 10 volts. I know that IR3 is VR3 divided by R3. Ohm's law says 10 volts divided by 3K. So 10 volts divided by 3K. So I have 3.33 milliamps. 3.33 milliamps. Again, I'm difficult time trying to keep this all on the same screen for you. Now, we know, we'll just call this Ix. We know from Kirchhoff's current law for parallel circuits that Ix is equal to I total minus IR3. So the total comes up, some goes this way, some goes this way. We just call this Ix for now. So again, circuit, the current splits, some goes this way, some goes this way. So Ix in this case is equal to 6.67 milliamps minus 3.33 milliamps. So Ix is equal to 3.33 milliamps. Now, Ix is the current that's flowing through that equivalent resistor. Where did that equivalent resistor come from? Well, it came from these two. So Ix is actually this current as it goes down that branch. And because these two are both in series, they share that same current. So Ix actually flows through R1 and R2. So IR1 is 3.33 milliamps. IR2 is 3.33 milliamps. Ohm's law will now tell us that the voltage drop across R1 is equal to IR1 times R1. Voltage drop across R2 is IR2 times R2. So now we're going back to the original circuit, pulling out these numbers. So that becomes 3.33 milliamps times 1K equals 3.33 volts. 3.33 milliamps times 2K equals 6.66 volts. Now, looking for a good color for this. Here we go. Let's try the black. Here to here. If I take these two values, Kirchhoff's voltage law for things in series states that if I add those two up, it should come to the total. So if I take VR1 plus VR2, because those things are in series, I should get V total. And that works out to be 3.33 plus 6.66, and that comes out to be 9.9999999, so 10 volts. 10 volts. So once again, we have solved for a combination circuit. So the first thing we must do is identify things in the circuit and then ask ourselves these two questions. Does IT flow through any single resistor? No, it splits before it gets to them. So therefore, this is a no. Does any resistor have the same voltage as VT? Well, here's VT, and I follow that up, and you find out that that voltage and that resistor are connected directly to each other. So that means that the voltage across this resistor is the same as the supply. So the answer to that is yes. So therefore, this simplifies down to a parallel circuit. How many branches do I have? Well, I have one branch, two branches. So that's what my parallel circuit looks like. One branch, two branches. Then I have to extract the series part, find an equivalent, and pop it into my parallel circuit. Then I can solve for as many things as I can here, and then work backwards to the original. And what we end up with are those. So we're going to be solving a number of these questions as we move forward with our studies. We'll be doing a bunch of them in the Live with Mr. G session in the coming weeks. But that is two basic examples of a series parallel combination. One of them resolving to a series, the other one resolving to parallel. So again, we're going to be doing a bunch more of these as we move forward. All right. So this is series parallel combination circuits. I hope this helps. Until next time, everybody stay safe. Take care.